So now see here, we just go for crystals defects. Okay. Now you can just see this, right? In the previous classes, we just had the different defects in the crystals. Now in today's class, we are going to have a derivation regarding regarding the equilibrium concentration of the Schottky defect in metals, right? So, what is the basic mathematical expression to find out the exact value of the what you can say, not exact value, we cannot find it exact value, but a probable value of the concentration, equilibrium concentration of Schottky defect in metals. So, for that instant, right, what we do is that we just consider a metal in which, let us consider the energy formation of a Schottky defect is denoted by the letter E suffix V, and N is the number of atoms in the metallic crystal. So here, let us consider that energy of formation of Schottky defect. So how this formation of Schottky defect is taking place? So what we are doing here is that we just uh, we are heating it. So when you heat it, what will happen? The energy will be formed, and that energy is nothing but we are just keeping it as EV. And how many numbers of atoms are there in metallic crystal? That is capital N. And maybe small n resembles the number of Schottky defects atoms, right? So now we don't know exactly what is the mm, how to exactly evaluate the number of Schottky defects. So we just take a probability concept, right? So the probability concept says that uh, the P is equal to S log W. So now here the as I said you that there will be a heat formation. You know that the phenomena of entropy will come into exist here. So the by using the permutation and combination phenomena, for the probability concept you already know in the lower classes. So the change in the entropy. So what is the entropy? Entropy is nothing but the disorderedness in the system which is caused due to the amount of heat, right? So the change in the disorder in the entropy is given by the formula S is equal to, okay, how many total number of atoms are there in the uh, what you can say in metal? Capital N is the total number of atom. So just we are representing it n factorial, and which is divided by the n factorial. Here, this is divided by, you can see, n factorial divided by small n factorial, right? Now, this is the basic formula uh, which is given in the uh, permutation and combination. The total number of atoms in the numerator and the number of atoms, right? The Schottky defect atoms are nothing but we are just writing it as small n factorial. So what is remaining? Capital N minus n small n factorial. So now is equal into k log p. So k is what? Boltzmann constant and log of p. So logarithmic of p. So now what is p actually? P is nothing but n factorial by small n factorial into n minus n factorial. Now that is the probability that we are assuming that this may be the probability to calculate the Schottky defect atoms from the total number of atoms, right? So now the second step you go. The second step, we see that S is equal to k log n factorial by small n factorial into sorry, multiplied with capital N minus small n factorial. Now, here we are very much interested in uh, uh, in the concept of simple mathematics. We are going to solve this by using simple mathematics. So, log of n factorial by small n factorial into capital N minus small n factorial. So this is in the form of log of a by b. So here we resembles that small a is nothing but capital N factorial and small b resembles small n factorial into n minus n factorial. So now, so usually we had a formula of log a by b as log a minus log b. So here when I say b is a combination of two terms. So that is the reason that in the later step, what we are doing here is that s is equal to k log a is what n factorial minus minus of the whole these two terms, right? So log n factorial minus log here you can just see this s is equal to k log n factorial by small n factorial into n minus n factorial. So here s is equal to k log n factorial minus of log n factorial minus log of n minus n factorial. So here, so this is in the form of log a minus this entire term. So minus of uh, log of n factorial minus log of n minus n factorial. Now what we are doing is that here you can just see we are using Stirling approximation. By using the Stirling approximation, we want to remove this factorial term. So in order to remove this factorial term, what we have to do is that we have to use the Stirling operation. So Stirling operation says that Stirling is the name of the scientist who says that you can just what you can write as Stirling operation. I will show you. See, this is Stirling operation, right? So what we are doing is that if there is n factorial here, so let us consider that as given by log x factorial is equal to x log x minus x. So Stirling operation says that this is what your x log x minus x. So here, if it is x here, so here I'm talking about n. So here by applying the Stirling operation, what we are doing here is that log n factorial can be written as n log n, right? X log x minus x. So x is nothing but here n. You can just see it is n. So n log n minus n. So now this is first term is over. We have expanded by using the Stirling operation. So for your reference, right? We just I will write it down here. We'll take help of the Stirling operation, right? We'll just write it down here. Stirling operation. We'll write. Now we get applying Stirling operation log x factorial as here x log x minus n. So here factorial. Now this factorial has been varied, right? So this factorial has been varied. Now you can just see this. Okay, remove this. Now you can be very. It is very clear. So log x factorial is x log x minus m. So we call that the applying approximation, Stirling approximation. So log x factorial is x log x minus x. So this log x factorial phenomena is applied to first term, second term, and the third term. So you just whenever you find the factorial, right? That factorial can be written as x log x minus x. So instead of x here, this is a general formula you can apply to the capital log n factorial. So here it will become the s is equal to k into n log n minus n. And for the second one, small n log n. So already minus is there, right? So what is the factorial term here? X log x minus x. So already minus is there. When minus negative term goes inside, so what will come? Minus n log n plus n. I think you are very much clear about this. Now, so minus is already there here again. So log of n minus n factorial. So we have expanded according to this particular term here. So capital N minus small n log of capital N minus small n. So x log x form, you can see instead of x, what is there? Capital N minus small n. So I have written here capital N minus small n log of capital N minus small n plus. Now again y plus, again there is a minus here. So this minus into minus will get plus. So n capital N minus small n. So what is the ultimate term that you got? X is equal to k into n log n minus, see here, this minus n, you can see minus capital N and this plus capital N get cancelled. See, this can be cancelled out. So minus N and plus N gets getting cancelled out. First term. So what is remaining here? Minus N small n log n. So I have written here after this minus n log n. Now here you can see again small plus n and here small minus n. This will get cancelled, right, everybody? So here minus n log n minus of what is remaining here? Capital N minus small n log of n minus n. See, again I'm repeating the same thing. We got this particular function here, log n factorial. So I want to expand this, simplify it, the log n factorial. So I'm using this Stirling approximation. This is a mathematical approximation of factorial, right? Whenever you want to expand it. So therefore we are just writing it as log x factorial is equal to x log x minus n. So wherever factorial is there, that particular term will be expanded in the form of this factor term, right? So instead of x, n is there. So therefore I have written here n log n minus n. I hope everybody is clear with this. So the minus is there. I'm just writing it minus here. You can just see minus. So what is there here? Minus n log n minus of n. So minus into minus plus n. So that is the reason that small n log n plus n. Similarly, this is the case for log of capital N minus small n. So here also I'm writing it as capital N minus small n log of capital N minus n plus n minus n. So here you will get this term, right? I said that minus capital N and plus capital N, right, get cancelled out, minus n plus value, and then here plus small n and minus small n will get cancelled. So what is the remaining term that you will get? N log n, right? K n log n minus n log n. So minus of n minus n log of n minus n. So now this is the term for which we get ultimately this. Now, so by using the thermodynamics, why we are using here thermodynamics? So thermodynamics says that, see, wherever you will find the amount of, see, and we talk about entropy. So definitely we'll have a function called free energy function, which is mathematically given as F is equal to U minus Ts. So what is F here? It is called free energy function, which has been formed, right? Right? Due to the disorderness which is caused in the metal, that is related to the entropy. So F is equal to U minus Ts, where U is the internal energy, which is nothing but, which is given as small n into EV mathematically. So small n is the number of atoms of Schottky atoms, and EV is the amount of energy, right? Which is energy formation. So of the Schottky defect. So see, and when you multiply this number of atoms with the energy of the Schottky defector, right? So U is equal to N into EV. So instead of, this is internal energy, which is given by N into EV. So S you already know. What is S value we got? See here. This is your actual entropy. So entropy is what is the disorderness which is caused in the system. So here mathematically this is a disorderness shown by the this particular step. So you can just write it. You can just see this U is equal to N into EV. So at equilibrium, right, at some constant conditions, so the amount of change in the free energy is a minimum, right? So at some constant, right, a constant state, at some constant state, the free energy is minimum, and which is given by the function, right? we'll use a derivative function. Wherever you find that we talk about minimum energy, it means that mathematically that should be constant. So you know that the differentiation of constant is nothing but it is 0. So therefore, this is the condition of minimum function of any function. If you want to know the minimum value, so therefore, we just know when you talk about change, right? We have just started change in the free energy. So that change in the free energy at the constant state is given by change. When you say change, differentiation will come. So therefore, that is the reason that mathematically we are just writing it as dou f by dou n, which is equal to 0. So when I write f you already know, right? What is f? This is the free energy function, mathematical function, which is given by u minus ts. So so you just differentiate it. So when you differentiate it, right? So with respect to small n, already you know this. Small n with respect to small n, you will get this value as EV. You can see this, right? U is substituted here, n into EV. So with respect to now f, dou f by dou n is 0. So dou f by dou n value we have written as 0 here. So EV minus TS, right? S is what here? So T I have written here. S is K. K into T as it is I have written. So now what is the term here? We just differentiate it. We are differentiating with respect to small n. The first term is 0. Everybody, I think everybody is clear with this because it is capital N and here also capital N. So this term, entire term will be 0. So therefore, this is 0 minus small n, right? So it is in the form of what you can say UV rule in mathematics. So what is U? Small n, and V is what? Log n. So U into dV by dx, minus is already there here. So U into dV by dx, differentiation of log x is 1 by x. Instead of x, what is there here in our derivation? N. So minus n into 1 by n, we can just see minus n into 1 by n. So now this is minus. Now V as it is written. What is UV rule? U into dV by dx plus V into du by dx. So what is U? N is U and V is log n. So we have just differentiated the first term here, n into 1 by x, that is 1 by n. So minus log n, right? So log x with the next term is V, dV by dx. So dV by dx means differentiation of n with respect to n is 1. So therefore, we can just write it down minus log n. Now, the next term, u dv by dx. So, uv, again uv. So, u is what? Capital N minus small n. And v is what? Log of capital N minus small n. So, what we are writing here is that u dv by dx. So, u is capital N minus small n. And dv by dx is 1 by x. So, log of x is what? 1 by x. So, here x means what? Capital N minus small n. So 1 by capital N minus small n. So when I say it is x, right? So we are not differentiating exactly with small n. There is another term capital N minus small n. So we have to differentiate n again, small n again. So therefore, when you differentiate the small n, you will get the value as minus 1. So we got this value as minus 1. Okay, everybody, this is very, very important here. In mathematics, you see, a small n is associated with capital N, but it is differentiable. So therefore, what we am writing here, what we have to do, as it is, I'm writing capital N minus small n. 1 by x is log x is differentiation of log 1 by x. X is capital N minus small n. Again, small n should be differentiated. So when you differentiate it, you will get minus n. So minus of right, minus of, see my negative sign, already negative sign, I have just inserted that negative sign while doing the differentiation. So minus log of n minus n. So when you again see, I said again when you differentiate n minus small n, you'll get minus. But this is very, very important for you. I think that this simple differentiation is there. So so now you got this value, right? It is very clear. Now EV minus KT, you can just see here. n's. This n and this n get cancelled, right? Okay, this n gets cancelled. What is remaining here? Minus 1. Okay, now this will just keep this minus 1 as it is. Now you can just see this is minus 1. I have kept minus 1 as it is. Now here capital N minus small n and capital N minus small n. Clear everybody? This term and this term get cancelled. So minus 1 into minus 1, that is what? Plus 1. So this entire value is plus 1. So this plus 1 and this minus 1 get cancelled. Clear? So what is remaining here? Minus log n. So here I have written minus log n. So next aspect, this is remaining. Okay. So minus into minus is plus. Therefore, we have written it plus log of n minus n as it is I have written here. See, this should be very much clear to you. See, in this step, n into 1 by n, negative sign is there, small n and capital small n get cancelled. In the numerator, small n is there. In the denominator, you'll find that small n. So this n and this n is getting cancelled. So minus 1 is remaining here. See, in the same step, this capital N minus small n in the numerator and capital N minus small n in the denominator. So definitely this and this get cancelled. So minus into minus is plus 1. Plus 1. This value, entire value is plus 1 now. This value is minus 1. Minus 1 plus 1 get cancelled. Okay. What is remaining? Minus log n this term. So minus log n as it is we have written here. Minus into minus plus. So log of n minus n. So when I just take out this EV outside, the EV is equal to KT minus log n plus log of n minus n. Clear everybody? So EV, so this KT term taken in the left hand side in the denominator. So EV by KT is equal to minus log n plus log of n minus n. So now you can very much, I think that you got an idea. This is log A minus log B. So what is log A? It is in the form of log A minus log B. So log of A is capital N minus small n. So therefore I have written here log A by B. When you say that log A minus log B is log of A by B. So this log will go to the left hand side and it will become exponential. So e to the power of EV by KT is equal to capital N minus small n by small n. So now you think that, see what we have written here, e to the power of EV by KT is equal to capital N minus small n. If, see, when I compare the number of atoms which are defective in metal, the number of atoms which are defective in the metals, right, is very much less than the total number of atoms. Definitely, yes. See, capital N is the total number of atoms and small n is the number of Schottky defect atoms, right? There's some defect and that defective atoms are very small when compared to the total number of atoms in the metal. So n is very, very small when compared to capital N. So what you can say, small n can be neglected. This term can be neglected. So instead of capital N minus small n, what you can write here? Capital N. I think everybody got this. See, instead of capital N minus small n, what we can write? Capital N. So here we have written with the capital N here instead of, why we have written? If we compare small n when with the capital N, small n is very small. So capital N is very large. Small n itself is very small. If I take out that very small value, so it will be that particular value can be neglected. So writing instead of capital N minus small n, can I write capital N here? So small n, see the small n, when you go here, this will go down. The small n go to the left hand side. E to the power of EV by KT comes to denominator. So small n is equal to capital N into, see, e to the power of EV by KT in the denominator. When you come to the numerator, automatically e to the power of minus EV by KT will come. So small n is equal to capital N into e to the power of minus EV by KT. Now, so this is the number of Schottky defect atoms which are present in the metal. This was a defective atoms which are there in the metals. So this is the way that how you can calculate a probable value of number of Schottky defect atoms which are present inside the metal. So this is given, this is n is equal to capital N into e to the power of minus ev by kt. So now this is what we are doing in the examination. They will ask you derive the equilibrium concentration of Schottky defect in metal. So right, so you can just write it down in this particular manner. So I will give you the notes, right? This is from notes actually what we have prepared you. This is the notes which we have prepared for you. So now in the same, when we talk about Schottky defect, I think that you got exact idea. So see, if you are not getting an idea, if you are not clear with the derivation, what I thought today, what you can do is that you just make a note of it. So in today's session, when you come to today's session or tomorrow and the next week, so when you are coming to the college, right? So though for probably we'll be calling the students to the college. So I will just derive this particular expression on the board also for your convenience. If you have not followed this thing, so no worries, right? So we'll just derive this particular expression on the board, and I think that you will have very clear idea regarding this. So whatever the topics that you have not understood in the class, right, online classes, we just make a note, everybody, and whatever the doubts are there. So when we come, when you come for the doubt sessions, right? So definitely one by one, I will try to clarify it by doing it on the board, or if it is feasible for you. So in whatever the way that is comfortable to you, so we'll try to sort it out your doubts. Understood, everybody? So you need not worry, right? If you are not following some, there are some queries regarding the that some students are not following. So no problem with that. When you come for the doubt session next week, so we'll try to solve all the doubts, right? Uh, but you need to practice, right? Engineering doesn't mean that you should modify the things, whatever it may. So you need to understand the concept very well, and then you have to apply that concept. Then only you can will be passing to the next level. So that is the reason that we are in this class. I'm going very slow. Why? Because this is dealing with the expression. So now the Schottky defect. See, this is the case for metals, right? We got this expression. This is the probable value of the Schottky defects, number of the atoms which are defective, right? So here again we are having an expression called equilibrium concentration of Schottky defects in the ionic crystal. So in the ionic crystal also you'll find the Schottky defect. So Schottky defects, what is that mathematical term that we are going to learn here? So what is Schottky defect? You already know. What is Schottky defect? Equal number of missing negative charged and negative and positive charged ions, right? From the crystal is known as Schottky defect. In general, I'm talking about. So equal number of positive and the negative ions, negative charge ions are nothing but we'll call that as Schottky defect here. So here now let us consider. See, there is no such ideal crystal, but for our, see, we are going for a probability value of the number of Schottky defective atoms, right? Probable value, right? So now for that, first of all, we are considering an ideal crystal. So consider the ideal crystal in which, say, EV we have taken for metallic crystal. Here I'm just taking it as ES suffix, capital E suffix S. So energy required to create this Schottky. Here we are creating a Schottky defect, right? So how it is created? By applying some amount of heat to the ideal crystal, right? Ionic crystal. So you apply some amount of heat, some stress is applied. So definitely there will be vibrations inside the crystal. So when you there is vibration of, see, what is that vibration? Vibrations of the atoms, the displacement of the atoms. So when the atoms are getting displaced, so that displacement is nothing but we are calling that as disorderness, and that disorderness we'll calculate with the help of a mathematical expression, that is f is equal to u minus ts in the latest section, in the same manner what we have done in the previous derivation. So method. So that is the reason that we cannot actually find out the number of Schottky defect atoms. So we are taking the help of probability concept here. So now that is the thing. So energy required to create a Schottky defect. Yes, capital N is the number of atoms, same thing, and small n is the number of concentration of Schottky defective atoms. So which concept we have to apply when you don't know exactly what is happening inside the system. So you go for some probability concept. So the probability concept is given by P is equal to capital N factorial by small n factorial into capital N minus small n factorial whole square. Now this particular term, why it is square? Because the Schottky defect in ion, we are talking about ion. So ionic crystal, Schottky defects in ionic crystal, equal number of positive and the negative charged ions. So the positive and negative equal number means we just write it down, the n factorial by small n factorial into n minus n factorial whole square. You can see this is square means equal number of the charged ions. This is very, very important. If you understand this, the term which is there here, that is very, very easy. Now, what is the change in entropy formula? This is S represent the entropy. Mathematically, the change in the entropy is given by the formula. Mathematically, S is equal to K log P, right? So, log, what is the P? You know this, capital N minus. So, why it is square here? In the case of metal, it is not square. You can see. In the case of metal, this is not square, capital N, because in metal, what is here when we talk about metal? Metal means you'll have the movement of atoms freely, right? So the atoms will move freely, right? And the here when you talk about ionic crystal, equal number of positive and the negative charge ions. So we talk about twice, right? Two positive charge and negative charge. Therefore, we just write probability P is equal to n factorial by small n factorial into capital N minus small n whole square. Now, the change in entropy derivation is given by S is equal to K log P. So, log P log of P. P is what? This particular term. So, n factorial by small n factorial into n minus n factorial whole square. So, now log of, see, this is log a to the power of n log a to the power of n. So what is it? N log a. N is what here? 2. So 2k log of n factorial by small n factorial into n minus capital N minus small n factorial. So here the same thing. Metal and ionic crystal, only difference is you'll find square here. Everything is same. So S is equal to 2k log of A by B. Same manner what you have done in the metal. So log of A by B. So log n factorial minus log of n factorial minus log of n minus n factorial. Same applying this Snelling operation and the same expression. See, 2k is there. Here you'll find no 2k. You see, there is no 2k here, right? Everything is same. You can see everything is same. N log n minus n log n capital N minus 1 and log of n minus n. See, everything is same here. What we have done in the previous derivation. So by using this law of thermodynamics, F is equal to U minus Ts. Again, U is what here? N into Es. So instead of U, we are writing N into Es minus T as it is we have written. S is what? 2K. 2K, same term. See, you can see this is the same term what I have written here. So at equilibrium, the change in the free energy is minimum. So now the same thing, 2kT, again U V, UV. So UV, the same time we had U dV by ds log of n minus n and so on. So same derivation, derivative part we have done here, U into dV. So we got this value, right? What we have done in the previous case, minus 1 plus 1 get cancelled. Here remaining minus log n log n. Same, see, you can just see that same aspect what we have done, right? So in previous expression, Es by 2kt minus log n log of n plus 1. So what is extra term here? 2 is coming extra. That's all. Everything is in log of. So here also small n is very much what you can say less than capital N, and small n is neglected. So small n is equal to capital N e to the power of minus equal. So now there is a this is you can just say this result, right? Small n is equal to capital N e to the power of minus es by 2 kt. This expression you can see. Small n is equal to capital N e to the power of minus ev by kt. So here only one thing is the difference here. You find everything is same as it is. You can just do. You can just practice it out. You can just see here. See, e to the power of minus es by 2 kt. The 2 term is extra for Schottky. See, I'm talking about only Schottky defect now, right? So in the latest class, we will just go for the what you can say Frankel defect. With that, we'll just complete our chapter 2. So once we complete our chapter 2, definitely we'll go for some revision, right? So physically, when you come to the next class, next week, probably the next week, doubt sections are there. So wherever you find any difficulty, or if it means that we shall, sir, we have not understood the things which has been whatever the explanation you have done in the last classes. So definitely I will try to uh, brief it in the physical doubt session classes, and we'll try to do from the starting point, right? So definitely you need not worry regarding the understanding part, but one thing is very clear: you have to understand it in a very clear way, and whatever the doubts you are having, that should definitely be clear. We'll clear all the doubts, which is uh, what you can say you are having. So now, with this, we'll just wind up our class, and definitely in the next session, we'll go for the last topic of the chapter 2, that is uh, Frankel defect. See, one thing that you may be having an idea that we haven't gone for any numericals, right? So I don't want to do any numericals in this particular class here. So I will do that numericals right in the next class. So we'll just end the meeting today. So okay, thank you everyone. uh, we'll meet in the next class, right? Thank you.